which I can state and then also give a sketch of how the proof can be modified for type A. Okay, so G will be a simple finite dimensional Lie algebra or Lie superalgebra. WKGF will be the W algebra at level K associated to G and some even nilpotent element F and G. And W lower K GF will be the simple quotient. And for this talk, it's convenient to always replace my level with the shifted level. So I'll use psi equals K plus H check instead of K. So W's psi GF will always mean the W algebra at level K equals psi minus H check. And similarly, W lower psi will be the simple quotient. And if F is the principal nilpotent, then I'll just write W psi G. Okay, so the first important duality, which Thomas stated, is the Fagan-Frankel duality. And this is only for principal W algebras. And it says that W psi G is isomorphic to W psi prime of the Langland's dual of G, where these levels, the shifted levels psi and psi prime are related in this way, where R check is the lacing number. The Coset construction, this is a general construction in VOAs that has come up a couple of times. So let's say V is a VOA and A is a sub VOA. The coset is just the sub VOA consisting of elements of V which commute with everything from A. And if V and A have Virasoro elements, LV and LA, then the coset has Virasoro element equal to the difference, LC is LV minus LA, so that the tensor product of A with its coset conformally embeds in V. Another duality that's well known and quite basic is the so-called coset realization. So this works when G is simple and simply laced. So if you take the affine vertex algebra at level L of G tensored with the simple one at level 1, it has a diagonal embedding of the level L plus 1 affine VOA. And you can consider the coset of this copy of VL plus 1G inside. And that's the same as the GT invariance in this tensor product. And this is, as a one parameter VOA, isomorphic to the W algebra, W psi of G, with this level. So what are trialities? Trialities are supposed to be generalizations of both of these results. So let's say that F is a nilpotent G. We complete F to a copy of SL2, an SL2 triple inside G. And you can consider the centralizer of this SL2. So this is some Lie subalgebra or subsuperalgebra A. And the W algebra will then have an affine sub-VOA of type A for some shift level psi prime. This psi prime is an honest level in my talk. Psi was a shifted level, but this is the actual level of the affine sub-VOA. And so for the purposes today, the affine cosets that I'll consider will be the affine coset of the full affine sub-VOA. Last time I talked about more general affine cosets, but we don't need to consider those. And actually, I want to go a little bit further. Sometimes I'll take the coset by the full affine sub-VOA, but sometimes I also need to, after doing this, take the invariance under some group of outer automorphisms. So sometimes this group of automorphisms is a Z2, sometimes it's a U1 or a GL1. But I won't change notation. I'll say what I mean, but then my C psi GF will always be either this coset or this coset invariant under this outer automorphism group. And trialities are isomorphisms between three different affine cosets that are seemingly unrelated. And sometimes one of them is a Lie algebra and the other might be a Lie superalgebra. So three different Lie algebras, maybe three different nilpotents, and also three different levels. So non-obvious isomorphisms of this kind, which unify and generalize some previous results, including Fagan-Frankel duality, this coset realization that I mentioned, then some other dualities as well, one of which Thomas talked about in his talk a minute ago, which we can call Fagan-Semikhatov duality. Okay, so I'm going to restate the result in type A briefly and then explain how the proof of it goes. So Thomas introduced these and talked about them also last time, the small hook type W algebras. So SLN plus M, you can decompose as SLN plus GLM plus a sum of some modules. So CN is the standard module for SLN, CN star is its dual, and CM and CM star are the corresponding modules for GLM. So we have this decomposition of SLN plus M, And I take my nilpotent to be principal in SLN and trivial in GLM. So it's just a zero nilpotent GLM. And this corresponds to the hook type partition where I have one big column and then a bunch of short columns of length 1. And so my shifted level psi is k plus n plus m. And I'll denote W psi nm for short to be this W algebra associated with this nilpotent. And Thomas mentioned how this unifies some well-known examples. So if m is 0, then this is just the principal W algebra. If m is 1, then it's the subregular W algebra. If n is 2, this was the minimal W algebra. And also if I take n to be 0, this is just if I take n to be 1, this is just the affine Lie algebra. There's no nilpotent, then it's trivial. So if m is greater than or equal to 2, the affine sub-VOA is of type GLM. It has some shift. And that's the same as a Heisenberg tensor, an affine VOA of SLM. So if m is 1, then this just becomes the Heisenberg algebra. And if m is 0, then there's no affine subalgebra. And when I take affine coset, then nothing happens. There are additional even generators in weights 2, 3 up to n. And then there are 2m even fields in weight n plus 1 over 2, which transform under GLM as the standard representation in its dual. And so there's some extreme cases also that I should define. So the case where I told you that when n is 1, we get an affine algebra, but when n is 0, then I have to define it differently. So when m is greater than or equal to 2 and n is 0, what I'm going to do is define it to be an affine SLM tensored with a rank m beta gamma system. So SM is just the beta gamma system of rank m. And this carries an action of SLM at level -1. So there's a diagonal action here of SLM at level psi minus m minus 1. And also W psi 0, 1 is just the rank 1 beta gamma system, and 0, 0 is C. This is so that my theorem I'm going to state holds in the extreme cases as well. There's also a family of W-superalgebras that have very similar properties. So here, for the moment, I'm going to take n not equal to m. And when n equals m, as Thomas explained, we have to do it slightly differently. So SLN/m has a similar decomposition, SLN plus GLM plus some modules, but these are now odd. And the nilpotent that I want is principal in SLN and trivial in GLM. And the level shift is slightly different here. V psi nm will be this W superalgebra with this nilpotent. And when n equals m, as Thomas explained, the SLN/n is not simple, so we should replace it with PSLN/n. And the effect is that the affine sub-VOA, instead of being a GLN, is now an SLN. And the extra Heisenberg that was there before now gives rise to a non-trivial outer automorphism group U1, which I then have to take orbifold of. Okay, so in the for these superalgebras, if m is not equal to n, the affine sub-VOA is again of type GLM. If it is, if m equals n, then it's of type SLN. And there are also additional even generators in weights 2, 3 up to n. This comes from the decomposition of SLN with respect to the principal nilpotent. And then there are 2m odd fields in weight n plus 1 over 2 that transform under GLM as standard plus dual. So everything is the same essentially, except the levels look a little bit different. And these fields that transform under GLM in this way are odd rather than even. And again, there's an extreme case. When I take n to be 0, I haven't defined that. When n is 1, this is an affine superalgebra. When n is 0, I'm going to define it slightly differently, but similarly to the even case. I'm going to take affine SLM tensor of BCE system rather than a beta gamma system. And then the 1, 1 case, I should take a symplectic fermion algebra. The 0, 1 case is the rank 1 BC system. BC systems is the same thing as rank 2m free fermion algebra. And then these two cases I take to be just trivial, just the complex numbers. Okay, so now I consider the affine cosets. And so again, when m is 0, there's nothing to do. So in both those cases, C and D are just the principal W algebra. I take the coset of this affine piece otherwise, and in the case where n equals n, I have to take a U1 orbifold as well. And then the statement of triality is that when n is greater than or equal to m, we have these three isomorphisms. And how should we think about this? Well, the case where I have psi and psi inverse is a generalization of Fagan-Frankel duality. And so in the case where I take m equals 0 in the first isomorphism, d psi n0 is just a WSLN. And here I also get C psi inverse n0. That's the Fagan-Frankel dual W-algebra SLN. So in the case where m is equal 0, recovers Fagan-Frankel duality. And then the isomorphism between d psi and d psi prime with the switching of n and m, that corresponds to the Coset realization. So in the case where if I take m to be 0 here, I said a moment ago that d psi n0 is W SLN. But what about d psi 0n? So if you go back to the way I defined v psi 0m, this was an affine SLM tensor, some fermions. If I take the affine coset, they have a diagonal action. Taking the affine coset is what I'm supposed to do here. That's exactly the Coset realization. I think I've left out a Heisenberg. This is an SLN coset, the way I've defined it, but the Coset realization statement, I mean, I could phrase this as I could put another Heisenberg and make this a GLM, make it the same statements. So these statements generalize in two directions. And the way this is proven is uniform for all n and m. So it actually gives another proof of Fagan-Frankel duality and the Coset realization from a completely different perspective. The original proof involved the free field realization, and this proof will not make use of the free field realization. It's quite different. And this was conjectured by Gaiotto and Rabchuk, as Thomas explained. Okay, so I'm going to break this proof up into 3 steps. So the first step is based on the discussion in my talk last time of determining strong generating types of affine cosets using invariant theory and the vertex algebra Hilbert theorem. So last time we showed that C psi nm was of strong generating type W23 up to n plus 1, n plus n plus 1 minus 1. So that means that there's one field in each of these weights that close under OPE. They close non-linearly, but they're strong generators in the sense that they close under OPE. And this was, how did we do this? We passed to some limit, which was a free field algebra. We used invariant theory, and then we argued that we could pass from the limit to the one parameter family, and the generating type remains the same. So I won't go through the details of this, but it's a very similar argument that d psi nm has strong generating type W23 up to n plus 1, n plus 1 minus 1. Okay, so again, it uses invariant theory. You pass to the limit. The invariant theory involves the first and second fundamental theorems for GL M, but now it's acting on a fermionic space, but you can apply the same results. Notice that, so I didn't write down the central charges here, but it's easy to check that this theorem, all 3 of these algebras have the same central charge. And then this shows that they have the same strong generating type, because the relationship between a C and a D is that I have to replace the C by an n minus m, the first entry. So if I replace n by n minus m, then you see that these generating types are the same. So that's very far from proving that these are isomorphic as VOAs. And that's typically not such an easy thing to do. One approach is to try to find screening realizations of all these, but this is difficult at the moment. Another very naive thing would be to try to show that they have the same OPE algebra. And that's essentially what we'll do, but in a very indirect way, where we don't have to actually know what the OPE algebra is. We only need a very small amount of data about it. So the idea is that these are vertex algebras of a certain kind, a certain type of generating set, and such vertex algebras under some mild hypotheses can be classified. So there is a universal object. It's a 2-parameter vertex algebra. So it's going to be defined over a ring of polynomials in 2 variables, C and lambda. C is the central charge, then lambda is some other variable. and it's a W infinity algebra, meaning that it's got one generating field in each weight 2, 3, all the way out. So it's not finitely generated, but it has many one-parameter VOAs that arise as quotients. The one-parameter quotients are in bijection with certain curves in the plane that I'll call truncation curves. And all VOAs of this type arise as such one-parameter quotients. So it's kind of classifying object for these VOAs. So what we're going to do is show that both of these affine cosets arise as quotients of this universal object. That means that they correspond to curves. And because the correspondence is bijective, it's enough to compute these curves explicitly. And if I can show that the curves are the same, then we have the triality isomorphism. So we'll show that the curves are the same, and these different parameters that appear here are different ways of parametrizing the same curve. Okay, so from the explicit formulas, we get triality. Well, we get it in most cases. There's a few extreme cases that have to be done separately, which I'll mention. For most cases, you get it from this statement. Okay, so let me say something more general before I talk about this universal object. So there's a very nice paper of de Sol and Katz from 2005, where they introduced the notion of nonlinear Lie conformal algebras. So I'm going to explain the main result in different language. So this paper is written in the language of lambda brackets. But what's so powerful about this paper is that it gives a new approach to constructing VOAs. Normally, VOAs are built from a small number of existing ones, like affine VOAs. And then there are these procedures for getting new ones from old ones. You can take orbifold, you can take Coset, you can take extensions. There are ways of getting new ones from old ones. Most of them arise starting from a small number of them. But this paper tells you that in some abstract sense, you can construct VOAs by generators and relations in the same way that you can construct rings as quotients of polynomial rings. Like commutative rings are all quotients of polynomial rings by some ideal. It's a similar notion. So nonlinear conformal algebra is essentially equivalent to the OPE algebra of some VOA, where you have some fields that close under OPE but non-linearly. And there's one additional property that one needs for the corresponding OPE algebra to be a nonlinear Lie conformal algebra. So in the language of fields and OPEs rather than lambda brackets, essentially it's the following. It's a set of fields where let's grade it, make things easier. Let's take all the gradings to be positive, maybe integer or half integer gradings. And you have some specified OPEs. So this is a finite sum. This AI nth product AJ is some normally ordered polynomial in the generators and their iterated derivatives. And the total weight of this should be di plus dj minus n minus 1. So I didn't write down what this is. It's some unspecified polynomial in the generators and derivatives. And then if I take three elements from my set of generating fields, there's certain identities that are imposed. So of course, in de Sol and Katz's paper, they're expressed in terms of lambda brackets, but I'm just going to translate them into language of OPEs. So the first one says something about how the derivative interacts with the nth product for all n. This one is sometimes called quasi-commutativity. If I reverse the order of A and B, then I have one term which is B nth product A, and then I have a bunch of other terms. This one measures the non-associativity of the normal ordered product. This one measures the failure of the normal ordered product, the failure of the nth product to be a derivation of the normal ordered product. So the top line is the derivative, what it would be if it were a derivation. This is the correction term. So these identities all have to hold. And then there's some other identities that are independent of the ones that I wrote down in this formulation. So these are the so-called Jacobi identities. If I take R and S to be greater than or equal to 0, then I have some identities that measure the failure of the Rth product to be a derivation of the S product. But here, S is not a -1 product, it's a non-negative product. So these I call Jacobi identities or Jacobi relations of type ABC. And they don't necessarily hold as consequences of the ones on the previous slide, but if they do, if you only impose those and then these follow, then your nonlinear, your OPE algebra is a nonlinear Lie conformal algebra. And then one can define its universal enveloping vertex algebra that I'll call UA. It has the property that it's freely generated by these generating fields. And it has a universal property that any vertex algebra with the same generators and OPE relations has to be a quotient of this universal enveloping VOA. So actually what they prove is much stronger than this. So it may be the case that not all these Jacobi identities hold as consequences of the previous ones. And then there's still a good notion of the universal enveloping VOA, but it's no longer freely generated. You have to mod out by the consequences of these. So if you write down this Jacobiator, because OPEs are normally ordered polynomials in the generators and their derivatives, this quantity will be as well. And if it doesn't vanish as a consequence of the other identities, then you have to kill this in all its quantities. And then you get a VOA that's not freely generated. So in a very general sense, you can begin with a completely arbitrary set of fields and OPEs and that satisfy the relations on this slide. And then there's always a universal enveloping VOA that comes from it that one can define. If I do this randomly, it's probably going to be just nothing. Probably everything will vanish and I'll get 0. But if you can get intermediate cases, and also the question of when the universal VOA is freely generated is precisely that these Jacobi relations hold as a consequence of the others. This is my reformulation of the results of de Sol and Katz. Okay, so what is this good for? This allows one to construct this universal 2-parameter W infinity algebra. So this is something which was expected for a long time to exist in the physics literature. And there's plenty of papers where this is mentioned, and there's computational evidence for it, starting in the 90s, and then there was some resurgence of interest in it more recently. And so a couple of years ago, I used de Sol and Katz's perspective to show that there exists a unique 2-parameter W infinity algebra of this kind. And my parameters are slightly different. There's some reasons why I choose, my lambda parameter is not quite the same as the one that is traditionally used. It's more suitable for working over polynomials and applying methods of commutative algebra. And it's also more suitable for showing that the algebra exists than the original parametrization. So it's generated by a Virasoro field of central charge C, and also a weight 3 primary field, which is traditionally normalized so that its leading pole is C/3. So this was done in some of the physics papers, so I chose to do it the same way. The drawback with this normalization is that you never can get just the Virasoro algebra as a quotient of this, because W3 will be, as long as C is non-trivial, then this thing will have non-trivial pole of itself, and it will not live in a maximal ideal. This can easily be corrected by passing to a suitable limit, so I'm not going to worry about that so much. So we have, so the algebra should be generated by L and W3, but not strongly generated. So I'm going to define some descendants. So W4 will be, I take this is second order pole, the one product of W3 with itself. So this is some element of weight 4, and I take that to be my weight 4 field. And then recursively, I define all these higher fields in this way. Again, this is not the traditional way of defining these higher fields, but it's convenient for the purpose of constructing this algebra. And then this universal object should be freely generated by these fields. So it has a PBW basis consisting of all the iterated products of these fields and their derivatives. And the structure constants, so these close non-linearly. The structure constants are all polynomials in C and lambda. And it has the property that all vertex algebras of type W2, 3 up to some n, satisfying some mild hypotheses, will all arise as quotients of this algebra. So this algebra classifies VOAs of this type. And so the idea is that you begin with the data that I have a Virasoro field and a weight 3 primary field. And then I want to normalize W3 in this way that I just mentioned. I define these WNs recursively, and I write down the most general possible OPE algebra with undetermined coefficients that's consistent with the weight grading. So all the terms that appear have the appropriate weight. And then I try to determine what these coefficients can be by imposing the identities. So the first set of identities is sort of easy to impose, and it is not much of a constraint. It tells you that if I know the OPE of WI and WJ, then I know the OPE of WJ and WI. And also if I throw in derivatives, that's determined. But so most of what's interesting is imposing the Jacobi identities and trying to determine what this imposes on my undetermined constants. And this is a method that's been around in the physics literature for a long time. I'm going to call it, it's a kind of a bootstrap method for constructing OPE algebras. So this has been used by many authors. And in the case where the number of fields is finite, it's more or less rigorous the way that it's been used, except that back in the 90s, the paper of de Sol and Katz hadn't been written yet. So we didn't know that from an OPE algebra, you could construct the universal enveloping vertex algebra. But in conjunction with de Sol and Katz's paper, this method is fully rigorous as long as you can take care of all possible OPEs. But for infinitely generated algebras, that's a little bit harder, and the methods previously to working with this W infinity algebra were not fully rigorous because it was only done for the first few weights. So the calculation I'm going to do in the next two slides was certainly done in the physics literature, I think even in 1991. So if you impose the Jacobi identities where I do type Wi, Wj, Wk. And here, if I is 2, that just means the Virasoro field, where the sum of these is less than or equal to 9. This determines some OPEs where the sum of the weights of the fields is less than or equal to 7. So, so here, for example, is the OPE of W3 with W3. So this data is completely determined. This part I impose by just saying that W4 was this descendant. The OP of L with W4 is also determined. And notice in these two expressions, you only see the central charge as a parameter. You don't see this lambda parameter yet. But you start to see this lambda parameter when the sum of the weights is 7. So the OP of L with W5, some of these, so this term, the second order pole is just 5W5. Well, because this is a Virasoro. And if you look at the OP of W3 with W4, the second order pole is just W5 on the nose because of my definition of W5. But a bunch of these terms now have this lambda. And this is all a consequence of imposing those Jacobi identities. So you can do this up to some point by computer, but it's not conclusive. You need an argument that shows that, that for all n greater or equal to 9, if I impose Jacobi identities of this type for I plus j plus k less than or equal to n plus 2, that uniquely and consistently determines all these OPEs where some of these weights is less than or equal to n. So this is the part which is somewhat involved to show that there's a recursive structure that allows you to make this conclusion for all n. So you can do this, and at the end of this, you get a nonlinear Lie conformal algebra over the polynomial ring in 2 variables. Just like VOAs can be defined over rings, you can also define nonlinear Lie conformal algebras over rings. And this algebra that I want is the universal enveloping VOA. It has some properties. So its weight 0 space is just this ring, polynomials in C and lambda. And it's, as I said, freely generated, so it's easy to write down the character of this. And it's also simple in the sense that I mentioned in my first talk. So being simple as a VOA over a ring doesn't mean that it has no non-trivial ideals, but it means that all the non-trivial ideals you can think of as coming from the ring, in the sense that if you take any graded VOA ideal, if you intersect the weight 0 piece, then you get something non-zero. Okay, so you can alternatively think of this ideal as starting from an ideal in the ring, quotienting out by this ideal, and then taking the maximal VOA ideal, which will then be non-trivial, and then taking the quotients. So it's simple in this sense, but if I take the quotient by some ideal in the ring, then you may not get something simple. So this sort of tells you where to look for interesting one-parameter quotients. What you should do is consider ideals in the ring, which I identify with the weight 0 subspace. And I should take prime ideals. And then I take the VOA ideal generated by this ideal in the weight 0 subspace. And then I take the quotient. So I take Wi, by definition, is this VOA over the 2-parameter ring, mod this ideal generated by the ideal in the ring, the VOA ideal generated by that. And this is now a VOA over the quotient ring, polynomials in C and lambda mod I. So if I choose my ideal randomly, then this will still be simple. It's simple for a generic choice of ideal. But there are certain ideals where this is not simple. And how do you determine these? Well, essentially, if you consider the Shapovalov form, if you take the weight n subspace and look at the pairing, you have a bilinear form where you take OPE that sends you into the weight 0 part. That's a symmetric bilinear form, and it's a bilinear form with values in the ring, so the determinant will be some big polynomial in C and lambda. The irreducible factors will be correspond to ideals where this degenerates. That's how you determine what all the possible ideals are where this thing becomes non-simple. And then I can take the simple graded quotients. So by definition, this VOA will now have a non-trivial proper ideal. I take the quotients. Okay, that's how I can get one parameter families from this. Okay, so let me state some kind of classification results. So let's say that I have some VOA W of central charge C, which is generated by the Virasoro field and a weight 3 primary field. I can normalize it in this way. And when I write down these descendant fields, and I check the Jacobi identities, Wi, Wj, Wk, where the sum of these weights is less than or equal to 11. If just this subset of Jacobi identities holds as consequences of previous identities, meaning that this VOA has the same OPE algebra as the universal one, maybe after specializing along an ideal, then this VOA will be some one parameter quotient, as I've written down. And this is something which is checkable. And notice that when I quotient by some ideal, it may no longer be of type W23 out to infinity. It may truncate. It typically does truncate at some point. It doesn't have to be freely generated anymore. It can truncate to something where if you look at the OPEs among just these n fields, then there are some non-trivial things that have to be quotiented. This variety, V of I, the variety of this ideal, I'll call the truncation curve. And this statement that I'll mention here is that there's this bijection for two prime ideals. These two are isomorphic as one parameter VOAs if and only if the ideals are the same. Okay, so this is the case of prime ideals where the truncation curve is a one parameter object. So these I should think of as one parameter rings. If I parameterize the curve, then I'll have a parametrization. So I should also consider maximal ideals. Maximal ideal is just, they correspond to points, C1, lambda 1. So let's say that I1 is the maximal ideal of C1, lambda 1, and I2 is the maximal ideal of C2, lambda 2. Now when I take the quotient of these VOAs, if I specialize along this ideal, that just means setting C and lambda to be constants. So now my VOA is defined over the complex numbers. It may not be simple, but I can have simple quotients. And I can ask the question, when are the simple quotients of two of these specialized at a point, C comma lambda, when are they isomorphic? Well, of course, they're isomorphic if the points are the same. So if the C's are the same and the lambdas are the same. So essentially, that's it. There's only a few other degenerate cases. If the central charge is 0, then there's no restriction on the lambdas. Then these vertex algebras just degenerate to the complex numbers. Of course, they're isomorphic. And also, if the central charges are both -2, then there's no restriction in the lambdas. These vertex algebras are both isomorphic to the W3 algebra with central charge -2. This means the Analogue W3 algebra. In all other cases, the isomorphism type is specified uniquely by the point C lambda. So why am I telling you this? Well, it gives you a criterion for when two such quotients can be coincident, when you can have a non-trivial isomorphism between two VOAs at special points. So if I have two of these one parameter quotients, so I1 and I2 are now prime ideals. Let's say that I'm away from these degenerate central charges, 0 and -2. You can ask the question, when is this one isomorphic to this one? So they have to have the same central charge. But this says that the only way this can happen is if the lambdas are also the same. In other words, we're at an intersection of the two truncation curves. A priori, there could be more such coincidences, but this tells you those are the only ones. Okay. So that's all I want to say about this universal W infinity algebra. So the triality theorem is going to come from the precise description, as I said, of the truncation curves for these affine cosets. So let me state these now, and then I'll talk about how this is proven. So, and notice that there's some restrictions on my M and N. So if M is 0, then N has to be greater or equal to 3 because these correspond to principal W algebras. But if M is 2, then I would get the Virasoro algebra, and that's not a W infinity quotient the way that I've set things up. So it's a small point that I'll mention later, but in most cases, the C psi nm is a W infinity quotient, except for a few extremal cases. So if m is 0, then n has to be greater than or equal to 3. If m is 1, well, if m is, I have to also look at the cases where m is 0 and n is 1 and n is 2. So I'll mention those later. So in all other cases, this is this simple quotient of the W infinity algebra along some ideal that I'm going to denote by I n comma m. So this is an ideal in the parameters, the rings, polynomials in C and lambda. But writing down the ideal in terms of those variables is very complicated and not so enlightening. It's better to parameterize it. So in the following sense, I'm going to parameterize the variety. V of I n m is my curve. I'm going to give you a map psi from, big phi is going to go from the complex numbers. Well, this is a partially defined map. There's some poles that I didn't make explicit here, but it's going to map the variable phi, which is my shifted level, to C of phi comma lambda phi, such that this point lies on the ideal, lies on this curve. Okay, so here's my parameterization. C of phi is given by this expression. That's just the central charge of the coset of the W algebra that you can easily compute. What's difficult is to compute lambda. And it turns out there's a fairly nice expression for it given in this way. Okay, if you want to eliminate the variable phi and write what the ideal is in terms of C and lambda, you can do this, but it's a big mess, not so enlightening. Okay, so this is my parameterization for this curve. There's a similar one for D psi nm. Again, there's some range where this makes sense. And I'm going to call my ideal JNM. And again, it's better to describe it via a parameterization. So I'm going to call this big phi D comma NM. Again, it's a partially defined map from the complex numbers to this variety. And it goes like this. You see there's certain things that you have to throw out, whatever the roots are, the poles of the denominator here together with 0 and -1. Okay, actually these expressions are very similar. You get these by replacing m by -m in this expression. So they're very closely related. Okay, so once you know these formulas, then they have the desired symmetry. So it's very easy to check. If you take n greater or equal to m, then big phi of dnm psi. So this, remember, has two coordinates. There's c of phi and lambda, c of psi and lambda of psi. These are all functions with two coordinates, but they both coordinates agree if you do this by change n to n minus m and replace psi by psi inverse. And here, if I switch m and n and replace it by psi prime, satisfying this condition. Okay, so once you see that these parameterizations satisfy triality, then you immediately get that we have this isomorphism, the triality isomorphism of vertex algebras, because of the bijection between the curves and the algebras. And then the extreme cases, you can check them by hand. So in one extreme case where I've got 2, 0, this is the case where these are just the Virasoro algebra. This is just the first isomorphism is Fagan-Frankel duality for the Virasoro algebra, and then the one with d psi and d psi prime is Coset realization of the Virasoro algebra. So this we already know, we don't have to do anything new. And then the remaining cases, these hold trivially because all these vertex algebras are just the complex numbers. So there's, again, nothing to prove here. Okay, so the proof of triality boils down then to proving these explicit realizations of these algebras as W infinity quotients. Okay, so you might assume that just because I know that this C psi, I'm going to focus just on C psi rather than D psi because the proof is the same. So everything I'm going to say in this proof will be about the C psi. So we know that it is the correct generating type, W23 up to something. But it is not obvious that it's a WC lambda quotient because one of the properties that we need, I said these were mild properties, but they still have to be checked. We have to know that it's generated by the weights 2 and 3 fields, and that's not obvious. It may be possible to prove this from the Poisson structure, but to me, it's not obvious. It turns out that it's true, but we have to do some work to prove it. Actually, this will be something that we prove after we determine that truncation curve, not before. So, but what I can do is consider the subalgebra of C, Xi, and M that is generated by the weights 2 and 3 fields. So this may not be the whole thing, but we don't know that it's the whole thing yet, but I can at least consider this subalgebra. And then, these algebras C psi tilde and C psi have the same Virasoro, and they have the same weight 3 field. The question is whether those generate everything. So at least C psi tilde is conformally embedded in C psi, and that means that the big W algebra is an extension of the affine algebra tensor C tilde psi. I know that it's an extension of affine tensor C psi because this is the coset, but it's also an extension of the affine tensor, this slightly, possibly smaller sub-VOA. Okay, so I can also check fairly easily. It follows more or less from character considerations that this C psi tilde is of type W23 up to T. So the issue is that the first fields up to T might close under OPE. You might not be able to generate the next bunch of them from those, but at least it has this type. T might be less than or equal to the place where the full coset truncates. So I can tell that this C psi tilde is a W infinity quotient. So I don't know that it's the simple quotient. It doesn't actually matter. I don't know that it's everything, and because I don't know that it's everything, it's not obvious that it's simple, but at least I know that it's a W infinity quotient. So I'm now justified in working with this algebra and assuming that it's a W infinity quotient and seeing if I can determine the ideal. So that's what we're going to do. So let's go back to the W algebra, and let me give, I think I gave this name before, that the even primary fields that are in weight n+1/2 that transformed as Cm plus Cm star under GLM, I'm going to call them G plus or minus I runs from 1 to n. So the G pluses are the ones that live in Cm, and the G minuses live in, say, Cm star. Okay? And so I know these are primary with respect to the Virasoro for the W algebra. So LW means the Virasoro for this W algebra. So this is just the statement that these fields are primary of weight n+1/2. Okay, and I can also assume that they're primary for the action of the affine VOA. What that means is that if you take the OPE of the affine GLM generators with these G's, you only see a first order pole, and that just captures the action of the Lie algebra. So this OPE just sees the fact that they transform in this way under GLM. Okay, so now let me give some names to the standard generators for this C tilde. So remember that C tilde, this is the subalgebra generated by weight 2 field and weight 3 field. I'm going to call the weight 2 field L in here, and I'm going to call, there's a weight 3 field that I'll call W3, and I normalize it in the standard way. And then WI's for I greater than 3 are the descendants, the same that I wrote down for the universal algebra. So this L is the Virasoro in the coset. It's the same as the coset Virasoro. So LW, the total Virasoro in the W algebra, then is the sum of the Sugawara Virasoro for GLM and the coset Virasoro. Well, the action of LW on the G fields is given here. The action of LGLM is determined by the action of just the affine algebra, the GLM. So I know this piece, I know the OPE of LW on the G's, and I know the action, the OPE of LGLM on the G's, and that determines the action of L. That's this coset Virasoro on the G's. So far, there's a certain bit of my OPE algebra that's determined from very little information. So what's more interesting is to consider the OPE of this W3 field in the coset with the G's. And it turns out I don't need all the G's. I only need to work with the highest weight vector. So I'm going to just take G plus 1 to be the highest weight vector, and I'm going to just call it G, and that's the only one I need to use from now on. So let's write down what the OPE of W3 with G can look like. So there's going to be a third order pole, a second order pole, and a first order pole. The third order pole, the weight is going to be the same as the weight of G, namely n+1/2. So the only thing I can possibly see is a scalar multiple of G. When I go to the second order pole, the weight is supposed to be 1 more. So I can have the derivative of G. I can also have different G's times different weight 1 fields such that the total Cartan weight is what it should be. And that's it. So if M gets very big, there are many, many other fields that one in principle should write down. The number of things here is not uniform in M, it's going to get very big. So it turns out I don't need any of these. If I needed them, I would have a big problem doing this computation. So we don't need any more information than just the coefficient of the derivative of G. Then if you look at the first order pole, this is supposed to have weight of G, n plus 1 over 2 plus 2. So there's a term where you take the WIC product of L with G. There's a term where you have the second derivative of G. And then there are many more terms where you can have some affine thing times the derivative of G, or something quadratic in the affines times G. And you can have different G's. The constraint is that the Cartan weight should be the same as the Cartan weight here. So there are many more terms that could in principle appear, but again, I don't need them, thankfully. And of course, the number gets much bigger when n gets bigger. So these 4 undetermined constants, A0, A1, A2, and A3, I leave these as constants. Everything else I forget about. And it turns out that one can determine these constants in a way which is uniform for all n and m by imposing some Jacobi identities. And so I'm not going to write all of these down, but I'll just write down 1 or 2 of them. So I impose some Jacobi identities of type LW3G. And again, when I impose this identity, there are many terms, some of which depend on these terms that I didn't put in. I don't want to consider all the terms. There's only certain coefficients that I care about that only depend on the 4 undetermined constants that I wrote down. And so here's one example. So if I take L, this Jacobi identity where I have R and S equal to 2 and 1, and I pick out just a certain coefficient, then I get this equation involving AO, A1, and psi, m, and n are entering as parameters here. So this is uniform for m and n and psi. I haven't seen lambda yet. I need to go a little bit further to see the lambda, which is what I'm trying to calculate. So I have to go a little bit further. So here I didn't write everything down, but you can find enough of these to eliminate, write the 3 of them in terms of 1 of them. That's as far as you can go with identities of this kind. Then I have to consider OPEs of the W4 field with G and the W5 field with G. And again, there's a lot of terms that are very complicated that I don't care about. I only care about the coefficient of G in the 4th order pole here and the coefficient of G in the 5th order pole here. And these again are some undetermined constants. And again, I should impose some Jacobi identities. And so I have to impose identities of type W3, W3G and W3, W4G. And here's one example. So this one's relatively simple because this is a circle 0, or 0 product. I get a slightly more complicated expression by picking out the coefficient of one term. And here you see that lambda enters. And I need to calculate a few such expressions. And I have some system of equations that I can then solve. It turns out you can solve uniquely for this BO and lambda, but only for AO and B1 up to sign. Remember that the other A's, H1, A2, and A3 were determined in terms of AO. So the formula for lambda is exactly the one that I want. So if I replace the central charge with the central charge for this algebra, then lambda will be expressed in terms of psi, n, and m. It's exactly this formula. So what's important about this calculation is that even though the OPE structure gets more and more complicated when n and m get large, none of that matters. This can be carried out uniformly at fairly low weights. That means that it's a feasible calculation to do. And there's a little bit of sign ambiguity in these terms, but that only reflects the fact that WC lambda has a Z2 action. It doesn't affect the isomorphism type. So what we've done from this calculation is we have shown, we haven't yet said anything about the full affine coset, but this piece, this C tilde that was generated by the weight 2 and 3 fields, this thing is a W infinity quotient. And we don't know that it's simple, but if I pass to its simple quotient, that is isomorphic to this simple W infinity quotient along this ideal. Okay, so I need the explicit form of this ideal in order to carry out the last step, which is that these two are isomorphic, meaning that C tilde is all of C. So in order to do this, I can calculate the, I want to find some coincidences between the simple quotient of this algebra and principal W algebra of type A. And so one of the things that's nice about having these curves is you can find intersection points of these curves. It turns out all the curves intersect at rational points. And if one curve intersects another, then at that point we have a coincidence. So there are more coincidences than the one that I wrote down, but this is the one that I need for this argument. So if I take the truncation curve VINM, that's the one for this algebra that I just talked about, and I intersect it with the truncation curve for VIS comma 0, S comma 0 is the one that corresponds to the W algebra of SLS. Then I get this isomorphism. And here, the only isomorphism only holds when I pass to the simple quotient. But C tilde lower psi at this point is isomorphic to the simple W SLS algebra at this point. And so this psi, remember, is a shifted level. So that means that the level is minus S plus this thing. It's S plus M over S plus M plus N. And you notice that this is a non-degenerate admissible level. So, well, maybe I have to pick, I want M and N to be relatively prime for this. So this is, but even if, yeah, so this will be a non-degenerate admissible level most of the time, and the weights of the singular vectors you can calculate in the W-algebras at non-degenerate admissible level. So in general, this is not such an easy thing to do. But in this case, this W-algebra has a singular vector in weight n plus 1, n plus 1, and no singular vector in lower weight. So what does that mean? Well, the WSLS, if S gets very large, we know that the W algebra has generating fields in weights 2, 3 up to S. It may or may not truncate below that, but it can't truncate any lower than the first singular vector. So the truncation will be at some weight S, it may be equal to S, it may be lower, but the biggest, the smallest it can be is this quantity. And this was the number of generators that we had in the full affine coset. So that holds the simple quotient. So that means that the universal one at that point can't truncate any lower than the simple one did. Well, it's specialized at this value, it can't truncate below weight n. Weight n is bigger than this. And so the same thing has to hold for this one parameter family. And from this, we can conclude that all the generating fields that were in C psi have to already be in C tilde psi, so they have to be the same. So therefore, this affine coset really is on the nose this quotient that I wanted. I mean, the W infinity quotient. And I can do the same thing for the W superalgebra. And I have to calculate the truncation curve, and then I look at some intersection points with principal W algebras of type A. I find enough such intersection points, and I'm able to conclude that the piece generated in weights 2 and 3 was everything. So that's overview of the proof of trialities in type A. Any questions before I talk about BCD types? Okay, so here the story is more complicated. You can't separate BCD types, but you have to look at the way that they interact. So I'm going to define 8 families of W algebras or W superalgebras in a kind of uniform framework that is similar to the way that we describe the hook type W algebras for type A. So let's say that G is a simple Lie superalgebra. It's always going to be either BC or D type Lie algebra or an OSP N2R. And I'm going to decompose this as a sum of 2 Lie algebras or Lie superalgebras plus some tensor product of representations. So A and B are going to be Lie subalgebras or Lie subsuperalgebras. A is actually always a Lie algebra. A is always either a B type or a C type. B can be anything. And so it'll have these 2 Lie subalgebras, and then row A and row B will be the standard representations of A and B respectively. So, and they can be either even or odd, right? It depends on what G was. Okay, so now let's say that FA is the nilpotent element, which is principal in A and trivial in B. And so I'm going to define W psi GFA to be this W algebra. So this is the one which is its principal in A. And as usual, this is my shifted level. So the level is psi minus H check. And then the dimensions, so if row A, DA will be the dimension of row A, and DB will be the dimension of row B. So case 1, I'm going to break this into 2 cases. Case 1 will be where A is a type B algebra. So it's going to be SO, say 2m plus 1. So then the dimension of the standard representation is just 2m plus 1. In case 2, A will be symplectic, it'll be type C, and dA is then 2n. In both cases, the W algebra has shape very similar to the case of type A hook-type W algebras. The affine sub-VOA will be type B. So I'll have dimension of B fields in weight 1 that will be an affine VOA of type B for some shifted level, I'll call xi prime. Then I have a bunch of fields which transform trivially under B, weights 2, 4 up to 2n. So now they're in even weights. And then in some weight dA plus 1 over 2, I have dB fields, and they transform as the standard representation of G, of this affine P is B. And they could be even or odd, depending on G. Okay, so all these algebras have sort of the same shape. And unfortunately, I'm changing notation. At the beginning, I said that my affine sub VOA was A, but now I'm changing to B, and A is playing a different role. A is the algebra where my nilpotent is principal. So hopefully that doesn't cause confusion. So there are 8 cases. And so I'm going to write down these cases, and I'm going to break them up into case 1 and case 2. So case 1, remember, was where A is a type B algebra. So 1B, the B means the type of the affine subalgebra. So B is also type B, A is type B, and then G is some type D. So that's what my W algebra is. And then I'm going to call C, Xi, NM, and then 1B means I'm in this case. I have to have many more sub-indices to indicate all the different cases. This will be this affine coset. And I have to take Z2 orbifold here. So in all these cases, whenever I take affine coset of either a Lie algebra of type B, D, or OSP, I have to take Z2 orbifold. There's always an outer action that I have to take orbifold by. If the affine algebra is type C, then I don't have to do that. Okay, so type 1C is the case where, again, A is type B, B is symplectic, and then my G is some OSP algebra. And so C Xi 1Z is this affine coset. It's the coset of the symplectic algebra inside this OSP, and I don't have to take an orbifold. 1D affine subalgebra is a type D. This is type B, and then G is also type B. And then there's 1O, where the affine subalgebra is an OSP 1,2a. And again, I have to take a Z2 orbifold. Okay, so there are those case 1 examples. Case 2 examples, my A, the algebra where I'm taking the principal nilpotent, that one is always going to be type C. So 2B means that the affine piece is type B, G is an OSP algebra. 2C means that the affine piece is a symplectic one. G is also symplectic. 2D is affine piece is type D. This is an OSP. And type 2O, the affine piece is an OSP. This is an OSP. So it's sort of complicated, but all these algebras fit into the general framework that I mentioned earlier. Now that I've introduced the other thing that I didn't write down is there are some extremal cases, just like in type A. There are a few cases where I had to define it differently. That's the case here. I won't write them all down, but I'll mention one of them in a moment. So now I can state the triality results. Okay, so there's, as Thomas said, there are 4 families of trialities. Let me organize them I'll organize them into 4 classes, and they'll each get a name. So the first class of these will be, I'll call 2B, 2B, 2O triality. So for all n and m, C Xi 2B NM is isomorphic to C Xi prime 2B MN. So I do this switch, and these are related. Unfortunately, I didn't write this in quite the nice form that Thomas did, but this is the analog of 1 over Xi plus 1 over Xi prime equals 1. If you solve for this, you see that it looks like this, except that I have this 2, which comes from the laicity. Okay, so this is some analog of coset realization. And actually, you get a kind of coset realization from this in the sense that there is one extreme case that I didn't define yet, but I'm going to define it now. So C Xi 2B N0. So N0 is the case where so I take M to be 0. Okay, that's the case where the part that should have had the principal nilpotent goes away. So instead of defining the W algebra in this case, what I do is I take affine SO2n plus 1, and then I tensor it with 2n plus 1 free fermions. And remember the 2n plus 1 free fermions has an action of level 1 SO2n plus 1. So there's a total action of level minus 2 xi minus 2n plus 2 SO2n plus 1, and I take the diagonal coset. That's the thing that should play the role of C xi 2b n 0. And this theorem is proven uniformly. It takes care of this case, even though this doesn't come from a Greenfield-Sokolov reduction. And by this triality, that's isomorphic. So this is a coset of an affine SO2n plus 1 inside something. That's isomorphic to the principal W algebra of OSP1, 2n, Z2 orbifold. So this gives you a coset realization of this orbifold, which is some analog of the coset realizations that we mentioned before and that Thomas talked about. So that's not the whole triality, that's just one piece of it. Another piece of it is that C xi 2b is isomorphic to C xi prime 2o with this shift and with this shift. And this is an analog of Fagan-Frankel duality, because this is sort of like psi prime and 1 over, this is a little bit like psi inverse, except that there's this factor. And then this is when m is bigger than n, and when m is less than n, there's a slightly different version of it. This one you should think of more like the coset realization rather than a Fagan-Frankel duality. And this first line, actually, if I specialize to the case where n is 0, so if I take n equals 0, then I know that this is a W principle of OSP1, 2n. This one is also, this 2o, you have to go back and look at what that was, but what was 2o in the case where n is 0? So yeah, if I take 2o, then this piece goes away, and this is exactly the principle. The nilpotent here is the same as the one here. This becomes the principal W algebra of OSP1, 2n. Well, I replace n with n. So this becomes a kind of Fagan-Frankel duality for. This is a shift of level, so this becomes a Fagan-Frankel duality for the OSP principal W algebra. Okay, so this is my 2b, 2b, 2o triality. So it says that a 2b is related to a 2b, and it's also related to a 2o, but I have to break up these into two cases, depending on whether n or m is bigger. Okay, and so there's some special cases that we can recognize. Okay, now I have 1c, 1c, 2c triality. So again, I'll write this as two different statements. So the 1c statement says that C xi 1c is isomorphic to C xi prime 1c if I switch n and m. Okay, and this one is a kind of coset realization statement. And here there's no factor of 2. So notice that if m is 0, then C 1c n comma 0, what does n comma 0 mean? This should be, my W algebra in this case is just an affine, because there's no piece where it's principal. Remember, if I had an M, it would be principal in some Lie algebra, but it's not, so I just have an OSP1, 2n, and this is just the affine coset. And then on the other side of this, I have the principal W algebra of type B, 1c, 0n. So you have to go back and look at what 1c was. So if m is 0, if m is 0, then what is this? G was OSP, this would be OSP1, 2n, and then we still have this piece, but then this goes away. So m equals 0 is this coset, and n equals 0. This is just, let me see. Make sure I'm saying this correctly. So if the first entry is 0, I'm sorry, no, this is, yeah, if the first entry is 0, then I want 1c 0n. That should just be a W algebra of SO2n plus 1. So let's see. If the first entry is 0, the n is 0, then yes, this is just OSP, this is 0, this is just SO2n plus 1. So that's right. So that what this gives you then is this isomorphism says that this principal W algebra of type B is isomorphic to this coset. So this is a coset realization for type B, and then also type C principal W algebras because of Fagan-Frankel duality. And I should mention that this was proven differently using screening realizations by Kreutzig and Genra. This gives another proof of this Coset realization for type B and C. It looks quite different from Coset realization for simply Lace types. So that's part of 1C, 1C, 2C triality. And then the other part is that there's an isomorphism of 2C and 1C. And this is more like a Fegen-Frankel duality. And then there's another family. This is the third family, 1D, 2D, 1O. So there's an isomorphism between a 1D and a 2D. And this one, again, if I specialize to n equals 0, I get the isomorphism between a W of SO2m plus 1, a type B, and a W of SP2m. And this shift over here is exactly Fegen-Frankel duality in type BC. For n equals 1, this one is a little bit more interesting. This is a relationship between the Heisenberg coset of a subregular W-algebra of type B and a Heisenberg coset of some subregular W-algebra of type OSP2, 2m plus 2. And this was proven by Kreutzig, Genra, and Nakatsuka. I'm going to call that Kreutzig, Genra, Nakatsuka duality in type B. And then there's another statement. So this one, in order for it to be part of this duality, I want m to be greater or equal to n, because if you consider the 2D algebra that appears, the second coordinate is greater or equal to the first coordinate. So for this 2D, the m should be bigger. This is isomorphic to a 1O algebra. And this one is like a Coset realization statement. And then the other one where I have 2D with the other direction where m is less than or equal to n, that appears in the last slide. This is, I'm going to call 1B, 1O, 2D triality. So again, there's an isomorphism between a 1B and a 1O algebra. This is like Fegen-Frankel duality. And if you specialize to n equals 0, then you get the Z2 invariant part of Fegen-Frankel duality in type D. And if I take m greater or equal to n, then this, did I get this right? Just make sure. Yes, because I've switched the relationship between m and n here. So, so a C xi 2D nm is isomorphic to a C xi prime 1O mn. No, I got this backwards, sorry. No, for 1O, the second coordinate should be bigger in this triality. So this should be n is bigger. This 2D with m smaller is the one which fits into this triality. And in this one, I can also specialize to recover the Z2 invariant part of the Coset realization of principal W-algebras of type D. So these are probably very hard to remember what all the notation is. So the slides will be posted so you can, I guess, see this more slowly. I certainly couldn't remember just looking at this, but the point is that there are more families of trialities in these types. They mix different Lie types, and they are generalizations of a bigger variety of results. Some Coset realizations. Sometimes I only see the Z2 invariant part of the Coset realization, and also some things that are all the Fegen-Frankel dualities, including for OSP12n. So these are all special cases of these general results. Okay, so let me say a few words in the last 20 minutes about how this is proven. So it's very similar to the outline for type A. So the first step is to use the Hilbert theorem and our general methods for computing strong generating types of cosets to find the generating types of all these affine cosets. Okay, so when I say affine coset, remember that sometimes I have a Z2 orbifold. So I'm going to just say, whenever I want to speak of these all at once, I'll call them IX. So I means 1 or 2, and X means B, C, D, or O. So it turns out that all of these things are of strong generating type W24 up to some 2n. Okay, and how do you show this? Well, again, you pass to a limit, which is a free field algebra. This can be handled using invariant theory. And the invariant theory is very nice because it's always, you have, when you pass to the associated graded algebra, it's a ring of invariants that's built from many copies of the standard representation, either of ON, n could be even or odd. So it's either orthogonal or symplectic, or in the case where the affine subalgebra is of OSP type, then I need the first and second fundamental theorems of invariant theory for OSP1, 2n. And this is very important result due to Alexander Sergeyev. This is a place where I have to apply that to get the generating type. So here's two statements of this kind. So the 1C coset, this is the coset of an SP2N algebra inside an OSP 2N plus 1 2N. This is of type 2,4 up to this quantity. And here's another one, here's a 2B. So this is now a coset of a type B affine algebra inside some slightly different OSP algebra. This is also of type 2,4 up to some quantity. So in all these cases, we can figure this out, and they're all of type W24 up to something. So again, just like the case of type A, there's a classifying object for vertex algebras of this kind. So this was something that was conjectured, I think probably much earlier, and then more recently by Candu, Gaberdiel, Kelm, Vollenweider in physics literature. And Shashank Kanade and I recently constructed this algebra. That there's a unique universal two-parameter vertex algebra that I'll call W even C lambda. So this is the even spin analog of the W infinity algebra I mentioned before. So it's freely generated of type W246 all the way to infinity. And all vertex algebras of this kind for some n satisfying some reasonable hypotheses are quotients. And again, the quotients come from ideals in the ring. So there are certain ideals where when I take the VOA ideal generated by some ideal I in the ring, this is no longer simple, and then I can take simple quotients. There's a corresponding variety, V of I, I'll call the truncation curve, just like before. There's a certain discrete family of such ideals where these things truncate. And so the main difficulty, we have to show that all these affine cosets, the C, Xi, I, X's, arise as quotients of this W infinity algebra and explicitly compute the ideals. So the first difficulty is that, well, we know that, so one of these mild hypotheses that I didn't write down is that you should consider algebras that are generated in weights 2 and 4. And so these affine cosets, a priori, we don't know that, just like in the type A case. So what we should do is consider the subalgebra generated in weights 2 and 4. That turns out to be some quotient of this even spin algebra for some ideal. And then we should try to characterize this ideal. And then at the end of that, we'll go back and conclude that these two are equal. So just like in the type A case, I know that the big W algebra is some extension of the affine subalgebra. And then this C tilde, which is some W infinity quotient. The extension is generated by some fields and some weight. They're dB fields, and this weight was transformed as the standard B module. And just like before, this can be used to explicitly determine this ideal. I have to set up certain Jacobi identities and be very careful which terms I pick, solve some equations. It turns out a little bit more complicated this time, but the same procedure in principle works. You get equations for these curves, and then I can go back and take the intersection of these curves with the curve for the type C principal W algebra, and that's the curve. There are many ways of realizing, but I1C0R is one such way. And there are many intersections now. It's not just like one family, but there are many. But there's one nice family of levels where this is non-degenerate admissible. And by finding the weights of the singular vectors, I can show that the truncation has to occur far enough out that C tilde has to account for all of C. And this is the end of the story. I can do this for all of these. And I get the explicit truncation curves. Okay, so that's the outline of the proof of this. Let me say a few words before the end about what these truncation curves look like and some features that they have. So I'm going to write down one of them. They're all fairly complicated, more so than the case of type A. Some of the complexity of this is because of the way I parameterize the algebra. I parameterize it in such a way where it's straightforward to construct this W infinity algebra and prove the uniqueness of it. But for the purpose of looking at its truncations, this is probably not the best way. So that's like, some of it is an artifact of the parameterization, but some of it is probably intrinsic to the nature of this algebra. I think it is more complicated than type A setting. So the statement is that the 2B affine coset can be realized as the quotient of this even spin algebra along an ideal that I'll denote by I 2B n comma n. And as usual, it's best to write down this ideal indirectly via a parameterization of the variety. So I'm going to write down a map phi 2b and m. So this takes the parameters psi, the shifted level, to c of psi comma lambda of psi. And these should lie in the variety. They should satisfy this ideal. And so the C formula is pretty nice. C of psi, this is just the central charge of this affine coset. The lambda is a little bit more complicated. So I'm going to write it as a certain rational function, f over gh, times a quantity that looked an awful lot like the lambda that I had in type A, where the denominator here appears in the numerator, and there's a little bit of small changes that take place. But these polynomials are rather complicated. This is f, this is g, that's not so bad, and h is not so bad either. And all the parameterizations, if I write down all these formulas for big phi of ix and m psi, they all have a similarly complicated expression. This one's actually a little bit easier. It's similar. So, looking at these, it's not obvious that they have any nice symmetry, but it turns out that they do. And one can verify, it's probably easiest to do this by computer, that all the trialities that I wrote down are simply symmetries of these parameterizations. So 2b, 2b, 2o is equivalent to saying that psi 2b and m satisfies this thing if I switch n and m, and this was what I called psi prime before. Here is 2b and 2o in the case where m is greater or equal to n, and this is m is less than or equal to n. And same thing for the others, so I'll maybe just go through this quickly. Our trialities are equivalent to these symmetries, which you can check directly. So even though the expressions are complicated, there's something nice about them, which is that they have these symmetries. Okay, so in type A, there is only one family of trialities. So even though I have two different kinds of algebras, I have these C's and D's, they realize the same curves. I just have different parameterizations of the same curve. And so it suffices to write down all the ideals in one shot, and then there are various presentations of reality. So one thing which is an open question that it's to me very intriguing, but I don't really know how to approach this, is that it's expected that all the one parameter quotients of WC lambda, meaning the ones where it truncates, where the ideal is if I take this ideal, then the VOA ideal the VOA becomes non-simple. That all the truncations that I found from these triality families account for all of them. So I don't know if that's true, but people believe that it's true, and there are various things one could do if you knew that. And it's interesting that you can express them all uniformly as one family. So for this other family, this BCDO, there are 4 distinct families of trialities, which I organized in this way. The ideals that appear in the first family are a uniform family that come from M and N. But none of these ideals is the same as one of these, et cetera. There are 4 distinct families of ideals. And so again, one expects that those 4 families account for all the one parameter quotients, but that's not known. Now there is an interesting computational observation, which is that these are different families of ideals, but there still is a uniform expression for all of them, which one notices computationally. So there are some identities that these parameterizations satisfy if you replace n and m with half integers. So n and m are not half integers, the way I've constructed these algebras, right? They correspond to the ranks of certain Lie subalgebras. So it's a priori meaningless to replace them with half integers. But it turns out that you can formally do this. If I take the 2b family, I wrote down the explicit formula for the 2b family. If I replace m with m minus a half, and I do a shift of level, I get the 1o family on the nose. And this just comes from the explicit formulas that I didn't write down. You can check these things. If I instead take the 2b family and replace n by n minus a half and do another shift, then I get the 2d family. And if I replace both of them by, in this case, I add a half, then I get the 1c family. So you see from this, I get something in all the triality classes. From 2b, I get 1o, 2d, and 1c. And then from the trialities, I get all the others. So you see that that all 8 of these equations, these parameterizations, can be obtained from one of them together with these shifts. So I would be curious to know if there's a conceptual explanation for what these half integer shift mean. There must be some, but I don't know what it is. But the fact that even though these are all, they give you different ideals, there's a uniformity in the expression for these. So I'm out of time, or mostly out of time. That's all I wanted to say. Any questions?
May I ask, is there any relation between this W of C lambda and centrally extended differential operators? Maybe as Lie algebras.
Say again a little louder, I didn't hear.
So, is there any relation between W of C and lambda and centrally extended differential operators?
Yeah, I think that there's a Poisson limit of the WC lambda that gives you the differential operators. I think that one is a quasi-classical limit of the other.
Maybe just
What?
Maybe just lambda go to infinity. Yes, it is.
Yeah.
Lie algebra, I think so.
Oh yeah. So there is the. Let me think. I don't think it's lambda goes to infinity. I think there's some other form. I think I wrote it in my paper on this. There's a certain specialization where you have to tensor with a Heisenberg for one thing to see this. And then,
Yeah, sure.
Yeah, and then it will be a Lie algebra in the sense that you can choose slightly different generators that now close linearly. So this is this usual W1 plus infinity.
Yes.
So yeah, it is not exactly lambda goes to infinity. It's something else, and it's I wrote it down, but I forget the formula for it.
But in this orthogonal case, it's a similar story. Something go to infinity, and we get symmetric differential operators, Q-symmetric.
That's right. There were these other W infinity type objects for the other Lie types that you can realize as specializations. And those also are one parameter algebras. Those are other one parameter specializations, but they're not the ones where it degenerates. It retains the same graded character, but it now has different OPE structure.
But are there two parameters in this differential operators? I mean, parameters of central extension.
Central extension, yes.
Yeah, I think that there is. The one that I know, if you take the differential operators on the circle, and then you take central extension, and then you take the corresponding vertex algebra, I think that only has one parameter. The central charge is a parameter, but then
and then you can deform it by lambda or by what? Yes.
Yeah. This you can think of as a deformation of that structure.
Thank you.
May I ask a simple question? Have these trialities you talked about before, have they been discovered before the main theorem?
The ones, the BCD type, I think so. So I believe that in the paper of Gaiotto and Rabchak, these, at least some of them are written down, but it's not completely obvious to me whether they're all there or whether it's exactly the same, but most likely they know about them.
Thank you.
Yeah.
And is this universal W infinity algebra of C and lambda related to the Lie category business? So I mean, one can consider, for example, in type A, one can consider the affine Lie algebra GLN hat as a Lie algebra in the Lie category of representations of GLN, for n being not necessarily integer. So one can recover. One can define a W algebra, corresponding W algebra via the Coset construction explained by Thomas. So is it the same thing or not?
I think it is the same, but I'm not quite sure. So there are some other ways you can construct this. So I don't know how to construct it using Drinfeld-Sokolov reduction in this way, but as a coset, you can construct it. So
yes, because the Drinfeld-Sokolov reduction cannot be defined in the link category, but rather the construction with tensoring by level 1 vertex algebra is well defined, I guess.
Yeah. So I think that what you can say is that it's similar, not exactly the same perspective, but if you take the coset of, say, GLN, affine GLN inside affine SLN plus 1. So you have a GLN sitting as this upper block of SLN plus 1. You can take this coset. So that's actually one of the trialities in our family. That's one of the affine cosets in our family. If you take the first coordinate 0 for type A, you get this family. So that is realized as such a quotient. But then if you think of n as analytically continued, you can replace n with a complex variable. Then that coset, I think, makes sense, and that will give you this 2-parameter algebra.
I see. Yeah, thanks.
Yeah, because what you can do is say that affine coset, if you fix n, there's a way of writing the generators in such a way that the structure constants are rational functions of n as well as the level. So you have to be careful how you write down the generators, but you can do it such a way that they close under OPE with n entering as a rational parameter. So then the fact that you can analytically continue it becomes clear from that. So you can sort of construct it as a universal enveloping algebra, some OPE algebra. This OPE algebra is defined kind of in some stable way, where if n is sufficiently large, you see all the OPEs up to some points. So if you want to see further, then let n be bigger. So you have a stable limit of OPE algebras and then take its universal enveloping vertex algebra. That's another construction of this.
Yes, thank you.
I have a couple of questions. In type A, in many cases, we have some information about the characters, at least of vacuum modules of the corresponding algebras. Do we have some nice basis?
So this would be at special levels.
Not special, generic parameter psi, but take some m and n, or even before. What can we say about basis of this? What kind of base do we have in the universal algebra? Of course, we have something like PBW basis, but do we have something base labeled by three-dimensional partition?
I think there's something that Thomas computed in our paper. There's something that one can say about the characters. I don't think that we know the characters of all these affine cosets. Maybe it can be computed, but I don't know. There's some information about this that Thomas worked out, but I don't know whether it's explicit enough. I don't know exactly what you can do with it. If Thomas is here, maybe he would give you a better answer than me. But yeah, I don't know if there's a good answer. I know that most of these affine cosets are not freely generated, so yes, the character is quite complicated. In fact, one thing that one can say from this, there's a kind of folklore conjecture that freely generated vertex algebras where the character is just a differential polynomial algebra are always, well, at least for finitely generated ones, should always be W-algebras. And so we have all these quotients of this W infinity algebra, and some of them are freely generated, namely the Y00n, the ones that correspond to W-algebras. And one thing that one can deduce from my description using invariant theory is that those are the only ones that are freely generated. So all the other ones, I can see that there are some relations, but exactly what the character is, I don't know.
No, Andy, but Misha is asking maybe about the existence of a good basis of McDonald Jack type labeled by Young diagram. What is happening in the A case? Yes, and or how?
I don't know.
I agree on any answer, but yes.
Yeah, I don't know. There may be in some papers of Prochaska some conjectures about this, but I don't know precise statements.
Mm-hmm.
Okay, I have maybe more technical question. Some arguments which you showed based on some calculations at some first levels, and I mean, such calculation. Do you use any software to do such calculations, or what?
Say it again.
Do you use any software for such calculations?
Yes.
What? Okay.
So
Can you comment?
So I use Thieleman's program, Chris Thieleman's program for doing OPEs, and so you have to be careful using it because some OPEs are not defined. If you haven't defined it, then it treats it as being 0. So you sort of have to know which identities, which OPEs you're allowed to use and which ones you're not. But Thieleman's program allows you to write down generators and OPEs and then compute anything that you want from that. And so the construction of these universal objects, in fact, the construction doesn't depend on computer calculations, but in order to know how to do it, I did a lot of computer experimentation and then saw sort of what the inductive pattern would be and then turned this into some kind of analytic argument. So the construction of universal objects you can do without the computer, but then these Jacobi calculations to determine what the curve is based on some small amount of data. This I can only do with a computer. I think in retrospect in type A, you could probably do it by hand, but in type BCD, it's impossible. Some of the equations you have to solve are very long.
And by the way, problem is how do you finally prove that the existence of universal algebra in type A? It was in the very beginning, but
yeah. So I mean, I only sketched it, but
yes, I did.
Yeah. So the idea is that you have to show that if you have Jacobi identities, you have to do this kind of inductively. So the first several stages you can do pretty easily. At some point, you have to show that if you know the OPEs up to, say, the total weight of the two fields is n, then if you impose Jacobi identities a little bit higher, that forces uniquely the OPEs at the next stage. And not just uniquely, but also consistently. So there's some difficulty, which is that you can't check all the Jacobi identities. You only check a subset of them. There's sort of a nice subset that one should check that imposes what the OPEs should be. And then there remains the question whether Jacobi identities that you didn't check might lead to inconsistencies. So what you do is it doesn't matter at this point, because even if they lead to inconsistencies, there's still, by Dessol and Katz's general picture, a universal enveloping VOA, where you impose some Jacobi identities, you have some universal enveloping object. If there are some Jacobi identities that fail, then you have to quotient something. A priori, this thing could vanish, it could be trivial. But then you show that it has many quotients. And so in particular, all the WSLN algebras are quotients. And because those are freely generated, then we conclude that there are no truncations, and therefore all the other Jacobi identities hold. So it's somewhat subtle. You have to actually work with potentially degenerate nonlinear Lie conformal algebras, and only at the end you can conclude that it's degenerate, that it's non-degenerate.
Thank you.
Yeah.
Other questions? No? So then, thank you very much for very interesting lectures.
Thank you.
So we'll resume tomorrow at 6 p.m. Moscow time.
Learn, and let's good to say that Friday we will have some discussion. Yes.
Yeah. So so another announcement is that on Friday at 6 p.m. again Moscow time, we will have some informal lecture / discussion by Sergei Gukov and Bora Fagin.
And all people want
and everybody is invited.
Invite to join and to discuss and in principle any question.
Okay.
Okay, thank you.
Thank you
So much.